Have you ever wondered how deep we could dig into the Earth?
No one's ever gone deeper than 12 kilometers, which is about 7.5 miles. That's deeper than Mount Everest is tall. And that took the Soviets 20 years. Still, it's just a scratch on the surface, a mere 0.2% of the way to the Earth's core. It turns out that the deeper you go, the more the Earth pushes back. But new technology could make it possible to dig further.
Whoa!
That's it. It just started to fly apart. Just so you could see how this rock became literally glass. And this could be the ticket to unlimited clean energy.
Just depths down to 6 kilometers that you could produce 1,400 gigawatts of new geothermal power. That's bigger than the current US power grid.
So can these drilling techniques make a 20-kilometer hole possible? And how far down can we actually go? Remember the space race between the US and the USSR? At the very same time, another race was underway. Not toward the moon, but deep beneath our feet. And this time, the Americans didn't win. The ultimate goal was scientific. The US started with Project Mohole in the 1960s,
which hopes one day to drill a hole through the crust of the Earth and to find out what's down there.
The idea was simple: drill through the ocean floor, where the Earth's crust is thinner, and reach the mantle. In theory, it was the fastest way down. To find a suitable spot to dig, researchers actually dropped bombs into the ocean.
3, 2, 1, 0. Over the side, over the side. The charge is over the side.
It doesn't get any more American than that. Then they used sonar readouts to measure the thickness of the Earth's crust.
But after years of work and millions of dollars, it made it just 183 meters into the seabed. That's less than 2 football fields. The project was eventually cut short due to lack of funding, but the techniques they developed led to a boom in offshore oil drilling.
Meanwhile, the Soviet Union began drilling on the Kola Peninsula in the Arctic Circle. Back then, researchers expected to hit 15 kilometers, about 9.3 miles.
But after 20 years of drilling, they reached a depth of 12,262 meters. That's deeper than the deepest point of the ocean, the Mariana Trench, located in the Pacific Ocean.
Since then, there have been oil wells that dug for longer stretches, like the Al Shaheen well in Qatar and one in Russia. But this type of exploratory drilling doesn't actually go straight down. These types of wells often veer sideways for long stretches looking for those reservoirs of hydrocarbons. So to this day, the Kola borehole remains the deepest vertical hole.
Kola was sealed with a metal cap and abandoned. It looks like this. One of the reasons the drilling was forced to stop is because the team encountered higher temperatures than expected. And this is the biggest challenge when it comes to digging deep: heat. Because the deeper you go, the hotter it gets.
As we get below sort of 12, 15, 18,000 feet, we're getting into very hot formations, very high temperatures where actual drilling tools are struggling to survive.
So if we want to go deeper than Kola, we need tech that can withstand temperatures that rise about 25 degrees Celsius per kilometer. Look at the geothermal gradient and you can see the heat increase isn't linear. Things get super hot long before you reach the mantle, a layer of Earth that no one has yet hit. As you go deeper still, temperatures can climb into the thousands of degrees. In fact, 99% of Earth's mass is hotter than 1,000 degrees Celsius. But that heat is also exactly what makes geothermal energy possible. Because if we can tap into it, it becomes a near limitless source of clean power. Right now, geothermal meets less than 1% of global energy demand. But if the technology keeps getting better, geothermal could cover up to 15% of the world's new electricity demand by 2050.
So how does it work? Inject water deep underground or dig into existing reservoirs. Then use heat from the Earth to turn it into steam. That steam spins turbines and generates electricity.
Unlike solar and wind, geothermal could provide electricity 24 hours a day and all year round. This is exactly what happens in places like Iceland, where volcanic activity brings a lot of that underground heat closer to the surface.
In Iceland, they actually made contact with magma at only 2.5 kilometers below the surface.
Iceland's large-scale shift to geothermal energy was driven by the 1973 oil crisis, when rising prices and geopolitical instability highlighted the risks of energy dependence. At the time, half of the homes relied on imported fossil fuel for heating, which was expensive for the country.
So Iceland turned underground. Today, nearly 30% of the country's electricity comes from geothermal, and about 90% of homes there are heated this way. And Iceland is not alone. Take a look at this map. Geothermal shows up all along the Ring of Fire, where tectonic plates converge. But there's a catch. Most places where geothermal energy works only dig down about 2 to 3 kilometers because that heat is close to the surface. Now, if we wanted to make geothermal work in more places, we're gonna have to go much, much deeper. That's why we're in Houston, Texas today, and we're going to a company called Quaise that's digging deeper using literal energy beams to vaporize rock.
All right, so this is where the magic happens.
This is where the magic happens. Quaise is a startup with a very ambitious goal. They want to be able to drill down to 20 kilometers underground. At that depth, the temperature can reach up to 500 degrees Celsius, which is enough to destroy any kind of conventional drilling equipment. That's why they're using something called millimeter wave. And the idea behind it is that it's using a special kind of technology that comes from fusion energy to literally shoot at the rock and vaporize it, melting it into glass. In the simplest layman's terms possible, what is millimeter wave drilling?
Millimeter wave drilling is using microwave to do dielectric heating to get to very hot rock.
Conventional drilling uses a mechanical bit to pulverize rock, but at extreme depths, it gets harder to power the system and it breaks a lot. Quaise uses electromagnetic energy to melt rock, and in theory, the millimeter waves maintain their power even over long distances. It took MIT over a decade to develop this technique in a lab. The device that creates the energy beam hot enough to do this is called a gyrotron, and it actually originates in nuclear fusion energy.
It actually is the device that converts electrical power to microwave power. That's important for us because it's able to make upward of 1 megawatt of microwave power.
You can see that the magnet's on because it's using electromagnetism. So apparently, I don't know what would happen. Would it suck? It would suck our cameras right to it, or
it could disturb some of it. Yeah.
Yeah.
We don't bring our phones in there. We don't
Right.
bring any kind of tools that are magnetic in there.
Oh, okay. So it could fly.
It's like an MRI machine.
Oh, it's like an MRI. So yeah, you know what? And actually, if you hear, I'm gonna put the microphone closer to there. If you hear, it actually sounds exactly like an MRI. If you've ever gotten an MRI, so listen to this.
That's actually the sound of the cooling system. The gyrotron's superconducting magnet needs to stay near negative 270 degrees Celsius to function properly. Quaise channels the beam through a hollow pipe that looks like it has screw threads inside.
So what you see here is the waveguide, and so the millimeter wave is actually going inside there, all the way to the bottom.
So basically, Henry, this kind of pipe is what's going to be going all the way down any hole you dig, right?
That's right. So we start with a conventional drill rig to drill as deep as they can, and then we come with our technology.
So the Quaise approach is less like drilling and more like burning a hole through the earth. In theory, this solves one of the biggest problems. If nothing touches the rock, nothing overheats.
The way we address it is that we're not putting equipment down hole that could be subjected to the temperature that could damage or that could fail the drilling process in that regards. And so we're not obviously eliminating the heat. Obviously we want to get to the heat, but we're able to continue drilling in spite of the heat in that regards, right?
Here's why they want rock that hot. At those temperatures and pressures, water enters a fourth state called supercritical. It's not quite gas and it's not quite liquid, and it carries far more energy than steam. Quaise says a single supercritical well could produce up to 10 times as much energy as a conventional geothermal project. And Quaise gave us a live demonstration on how they plan to reach it.
We're gonna put in earplugs, not because of the millimeter wave, but because the compressed air that comes in to the system is very loud. So I'm putting in earplugs right now.
Whoa!
Isn't that insane?
The light is completely bright. I guess you can see how the air is pushing all the other stuff out of the way. Wow. Okay, 30, he says 30 more seconds to go. Wow, that's pretty cool. That's it. Oh man, that's so cool. And you could see it's like lava cooling, right? I would say the heat hitting my hands right now is probably like, you know, a campfire that has died down. Not hot, not too hot to touch. I could still hear it crackling, which is kind of gnarly, but we're gonna, just so you could see how this rock became literally glass. If the drilling thing doesn't work out, maybe you guys can like use this to like get into a bank vault or something, I don't know.
Well, we said that we could just make ashtrays. I know people don't smoke anymore, but that would be an awesome ashtray.
To understand what they might encounter deep underground, Quays hauls huge chunks of rock into the lab. We're out back of the lab now. These are 10,000-pound lobes of rock, and they represent the different kinds of rock that Quays might encounter once they start digging down. They use these for testing, and they're very heavy and very expensive to get here. How the hell do you move these things?
It is incredibly expensive. Obviously, you need a big forklift that can actually carry the weight. But it's also incredibly expensive in terms of just getting it from the quarry of this size to us as well. And it's just part of the business.
But even if you solve heat, there's another problem: pressure. There are even more challenges that you have to deal with when you're digging super deep. And in order to show you what that looks like, we came to the Weiss Energy Hall here at the Houston Museum of Natural Science. So we're gonna take you around and show you a couple of exhibits that show you in a way that you can't see anywhere else. So what you see above me is a gigantic representation of a drill bit coming down a borehole. Obviously, this is probably, I don't know, 30, 40 times the scale, but it gives you a sense of how these rotating bits create a momentum going down into the hole, removing material and pushing it out towards the sides. So once you're getting down deeper and deeper, the rock isn't just hot, it's also heavy. That's what engineers called lithostatic pressure. At 10 kilometers down, you're under 40,000 pounds of pressure per square inch. You're basically trying to hold something open that wants to close. So what engineers do is something that might seem counterintuitive. They're actually filling the holes that they dig with drilling mud. And this drilling mud does three things. First of all, it cools the bit. Second of all, it lubricates the entire system. And third of all, it counteracts the pressure that's acting on the borehole as they go deeper and deeper. What this display is showing is that this mud has a viscosity that's meant to slow down the flow of the balls going downwards. And you could see how getting that and dialing that in just right is important to keeping the borehole stable. As you go deeper, something even stranger happens. The rock stops acting like a solid block and starts acting more like plastic. That's where casing comes in, because it's holding up the sides of the borehole as you go down and allowing you to drop a narrower and narrower channel of pipe down to reach those deeper depths. So as you could see from this example, we've started out with the widest possible drilling bore, which is 16 inches, and it goes all the way down to 5.5 inches.
Quays believes their system could also solve the casing issue. As the rock melted by the millimeter waves cools, it solidifies into a glassy lining around the borehole. That creates a hardened layer that will help keep the hole stable.
Just to feel the texture of it is that I do feel that volcanic glass feel. It reminds me of, when you had a piece of obsidian. If you ever had a rock collection at home, that's really what it feels like.
In other words, it's a sort of ready-made casing. But can this work at extreme depths? Over the years, Quays has proven they could dig past 100 meters, and now they've set up a test site in Marble Falls, Texas, where they're aiming to reach 1 kilometer by the end of the year.
We really want to show that we're going to do 1 kilometer, and it's really to show that we're very close to our goal of 10 kilometers. It's a 10x more, but 1 kilometer really gives you that depth where it is a viable option from a field point of view.
We hit the road to find out. This morning, we were heading from Houston, Texas, where Quase's lab is, to their test site in Marble Falls, which is on the other side of Austin, where Quase is actually bringing their technology to life in the real world. I'm standing at the edge of a granite quarry, and you could see why Quase would select this site to test their technology. Behind me, you can see that there's layers of sand and clay that have accumulated. That's called overburden. But not much further down, you've got this nice pink granite everywhere. And what Quase is able to do is, without digging too deep, they're able to get to this granite layer and start using their millimeter wave drill to really get through it. This is a perfect site for Quase to start proving that their technology works on the hardest rock that is found in the deepest layers to get to that supercritical geothermal. This is the first location where Quase has taken their technology out of the lab setting and into the real world. And obviously it's a work site, so I gotta have my hard hat and my safety glasses here. Okay, let's go. The gyro rig here can run on diesel, but for now it's connected to the grid. I wonder what your monthly electricity bill is.
It's not great.
So Steve, this hole is going to be the 1 kilometer hole?
That is correct, yep. So we'll be up and drilling in about 6 weeks, and then we're expecting to hit it in the summer. So we're talking maybe 2 months to get to 1 kilometer on this.
They're gonna take this wireline camera and they're gonna drop it down the hole that's existing. So we're gonna get an inside peek into the beginning of the 1 kilometer hole. What's interesting though is that the sides of this don't look like what we saw in the lab, like more vitrified. Is there a reason for that?
We are able to go that route as well. It's faster without it.
So you don't need that hard shell to prove the point of what you're doing.
That's correct.
Got it. There's another problem with drilling deep into the earth. We don't actually know what's down there. Most of what we can tell about the inside of the earth comes from seismic waves. How they travel and bend or slow down or speed up tells us what the different materials could be under the ground. We saw how some of this seismic exploration works at the museum. So you could see on this cube, it's representing different layers that could contain hydrocarbons, which is more for the traditional, conventional fracking industry. But this is the kind of seismic survey that you might see to understand what's below as you go deeper and deeper into the ground. And this is also part of this demonstration.
Yeah, this is a real piece of, they call it scenic sandstone, and this is a real geophone. This is one of those things that they stick in the ground. They just sort of drive it in like a stake, and then it picks up sound waves. So this is a clapper here. You can see this is a sound readout, and that's picking up kind of all the way across the frequency spectrum. This is going from 200 hertz up to about 1500 hertz. And you can see if I stomp, it's making more of the lower frequencies because I'm stomping, but it's picking it up. I mean, it's pretty sensitive.
But scientists keep discovering new layers, like the potential of a core inside the core of the Earth. For example, when scientists started the Kola Superdeep Borehole, they thought they'd know what they'd hit. Based on seismic data, they expected to find a layer of basalt. Instead, they found water and hydrogen gas. In the US, the deepest hole ever drilled, the Bertha Rogers well in Oklahoma, had to be stopped when it hit molten sulfur and broke the bit. So the deeper we go, the less certain things become, and every surprise pushes the machinery to its limits. And all this drilling can create unexpected outcomes, like earthquakes.
I would say that if you want to create an earthquake, you can create an earthquake. But there is a really widespread engagement with the fact that that is totally not an acceptable outcome.
In November 2017, a magnitude 5.5 earthquake struck near the city of Pohang in South Korea.
Later investigations concluded that it wasn't a natural event. Rather, the earthquake had been triggered by an experimental geothermal project.
The quake left 1,800 people displaced and 135 injured. It also caused at least $123 million in damage.
The nation's energy ministry expressed deep regret and said it would dismantle this project. Prior to that, the most notable earthquake induced by exploration for geothermal was in Basel, Switzerland. In December 2006, a 3.4 magnitude earthquake led to minor building damage. But the operator's insurance company paid out over $7 million in claims and eventually shut the project down.
What about this idea that drilling, I mean, any kind of drilling, but this idea that drilling can create seismic activity that can create earthquakes, and how do you mitigate that?
Yeah. So to be clear, the drilling aspect of it doesn't create any type of seismic. It's obviously when you try to do what we call the EGS aspect. When we're actually connecting between the two wells is where potentially you could have these type of issues. Now, the oil and gas industry has matured this significantly where now there's a regulation in place, there's sensors in place to make sure that you never go above a threshold that's unacceptable in that regards. Really, that threshold is the same threshold as what you typically see in a football game or a rock concert. That's the threshold which basically the standard is now. We don't go above.
In terms of a vibration.
In terms of vibration, things like that. So it's very well managed in terms of the level which is acceptable in that regard. So we never cross that threshold.
Another challenge for expanding geothermal is cost. Drilling deeper is slow, risky, and more expensive with every kilometer. Because it means more rig time, more crew, more wear on equipment, and more of a risk of failure. In fact, most of the time in conventional drilling is spent pulling up the rig and replacing a damaged bit. The core problem is upfront cost and uncertainty. You have to spend tens to hundreds of millions of dollars before you will know if a well will actually produce usable energy. That makes deep geothermal difficult to finance compared to solar, wind, or even conventional oil and gas. Historically, projects like Kola cost on the order of $100 million, and that's not even adjusted for inflation.
So the economic constraint isn't just, can we drill deeper? It's, can we drill deep enough, fast enough, and cheap enough to compete with other forms of energy? That's a yes, according to the CEO of Quaise, who recently testified at a congressional hearing.
So normally when you're drilling, you are trending in the $1,000 to $2,000 per meter. That's typical in oil and gas. It's cheaper in mining because it's a different use case. So what happens though when you go deeper and hotter is that $1,000 to $2,000 per meter starts to blow up exponentially on you. To give you a sense, you can get as high as $10,000 to $20,000 to $30,000 per meter to continue to make progress once you're below 3, 4, 5 miles. So we're trying to just skip that $1,000 to $2,000 per meter regardless of the depth, because that's what makes it economically viable and accessible.
And Henry told me that once a Quaise geothermal plant is up and running, it will prove more economically viable over time. The industry term for that is levelized cost of electricity. It's basically the cost per unit of electricity that a project needs to break even over the course of its lifetime. Quaise has an LCOE calculator on their website, and what it does is it allows you to go to a map of the United States, put a pin anywhere to get a cost of what a geothermal project would have in your area. It bundles everything into one number: the upfront costs to drill and build the project, the ongoing maintenance costs, fuel costs, financing costs, and basically the overall lifetime output of that energy project.
The amount of cost to drill a hole is about 20% of the overall cost of making geothermal. So the better answer is we think that the way we're going to make electricity, we can get these levelized costs of energy down to about $50 an hour, $50 per megawatt hours.
A price point of $50 per megawatt hour would make geothermal very competitive with new wind and solar projects.
Do you think that your first commercial project would come close to that number?
We think our first project up in Oregon will be about $100. And then by the time we get to the end of a kind, we're down to 50.
So far, investors hesitate to back up such problems. And the paradox is that because the costs are high, it hasn't scaled yet, but it won't scale without investment. So how do you break that cycle? This is where oil and gas comes in, because geothermal isn't completely new. It's built on top of an industry that already exists. Up to 80% of the investment required in a geothermal project involves capacity and skills that are common in oil and gas. And today, a large share of that workforce comes directly from the oil and gas industry.
There's 2,000 rigs around the world. With all the rig hands and all the people that know how to operate it, we basically give them a new set of tools.
In fact, some of the people we met here working for Quaise come from fracking. We're in the drilling cabin, AKA the dog house, and I'm here with Mike, Ethan, and Sam, and these guys are on site. They're living nearby 15 days out of the month, 5 days off, but they're committed to this site and they're gonna be the ones that are making sure that this hole goes down to 1 km. So I just wanted to talk to you guys because you guys could be part of a new wave of energy. Do you ever think about that and like what that might mean for, you know, for the future of everybody?
Supercritical seems like the major unlock to take geothermal to the next level. and there's some companies dabbling in it, kind of researching it. Quaise attracted me personally just because they're full on committed to making super hot, supercritical happen.
All the basic tools are the same. The expertise is similar. And even the techniques like horizontal drilling and hydraulic stimulation come from fracking, which means if geothermal scales, it'll likely use oil and gas infrastructure. And that matters because oil and gas is one of the few industries with the capital, equipment, and experience to drill at this scale. And we're already seeing interest. Chevron recently announced a joint venture with Baseload Capital. They have a fund focused on US geothermal development opportunities. Aramco announced they'll look into geothermal in the Middle East, and the current presidential administration has opened up public lands to a number of geothermal projects. But so far, investment has been limited compared to the trillions spent annually on fossil fuels. The industry is still waiting for a breakthrough, and until that changes, deep geothermal isn't just a technical challenge, it's a financial one.
So instead of going deeper, some geothermal companies are changing their strategy entirely.
I would say the main reason we people haven't gone deeper is there hasn't been a reason to. You know, oil and gas is found in shallow areas, and so the only reason to really drill past 10 kilometers is, you know, do a research well, and I'm sure you found a couple examples of that.
Companies like Fervo are not trying to drill to extreme depths. Instead of going as deep as possible, they focus on creating more contact with the heat that's already there, where the heat is still useful, but the engineering is far more manageable.
And so what Fervo does is we'll drill down into rock that's 400 or 450 degrees Fahrenheit. And then rather than just leaving a simple vertical well that might only be a few inches in diameter, try to produce heat from that section, we'll turn and drill horizontally for over a mile.
That process increases the surface area that's exposed to heat, which means more energy can be captured. So then they pump water underground at extremely high pressure, cracking open the rock and creating a network of tiny fractures. And through those fractures, water can flow. It moves through the hot rock, heats up, and is pushed back to the surface. It's a process borrowed directly from fracking. Out in the Nevada desert, Google has already signed a deal with Fervo to help power its data centers.
You're going to be hooked right into the AI data centers soon, right?
Yeah, that's where all the new market is going in energy these days, is trying to figure out how do we power all this new development from AI and do so in a way that's sustainable and affordable. And geothermal has a huge role to play in that.
So Quaise has a goal of drilling the world's deepest hole, and they have a plan to get there. But some of the experts I spoke to remain skeptical.
People like Quaise have got a very, very steep road. I don't think that we're going to see a successful supercritical project in the near term.
Quaise is still 5 years away from commercial operations at their site in Oregon. And then there's the issue of whether or not using gas to return powdered rock to the surface is even viable after a certain depth.
What you see is that drilling on air can be a really effective way of getting down through some challenging formations that, frankly, mud-based systems struggle with. But there are limits because as you go deeper and deeper and deeper, it's harder to return that to the surface.
So the deepest holes that I've ever heard of that have been air drilled, which is the same, you know, they're destroying the rock in a different way, but they're blowing it out of the hole as fine chips and dust, is about 10,000 feet. And that is pretty expensive to do.
Then there's the idea that any geothermal project using heat to generate electricity is incredibly inefficient.
As we take that working fluid and vaporize it and spin a turbine, a large amount of the energy that's present in that initial fluid escapes to the atmosphere, essentially as a required cooling stage that we have to do to make the power plant run. And only a relatively small amount of the initial energy is available in the final product, which is electricity on the grid. We're probably today with modern technology at about the 15% efficiency range.
So according to Wayne, the best use of geothermal is for direct heating and cooling.
If we're taking that geothermal energy and we're using it directly to warm something up, whether it's our living space or our dairy barn or our beer operation, we can dramatically improve the efficiency of the system. And instead of taking 15% of the energy, we could use something more like 85% of the energy.
That's what his team has done at Cornell University. Instead of traditional air conditioning, they use a passive system that's connected to Cayuga Lake,
where we allow heat to flow from campus to the cold, deep water of Cayuga Lake. And in doing so, completely bypass the efficiencies that are available with any other type of technology. So the cooling system that's in place today is probably 6 to 8 times more efficient than the world's second most efficient cooling system.
And finally, you don't actually need to go to 20 kilometers to access supercritical geothermal.
There's no reason from a point of view of having to produce usable heat to go to 20 kilometers anywhere on the face of the earth. It's too deep. From a science point of view, yeah, I could view it as, the analog to going to outer space. We're going to go to inner space and try to understand the earth better there, and we may discover some new things. But to claim that it's going to produce economic geothermal energy isn't necessary.
But maybe that's not the point. We're always going to wonder about the world beneath our feet. So how far can we actually go?
Oh, I don't think there's really any limit. We could go a lot deeper. It's just a question of what's the purpose and who's going to fund it. But it's definitely not a technological limitation.
I'm literally in the hole of a side of a cliff. Just another stupid thing I'm doing for a YouTube video. Look how deep that hole goes.